Okay, welcome to section 1.3, Solutions of a Linear System and Matrix Algebra. There are quite a few objectives in this section, quite a few things we are going to talk about with some propositions and proofs as well that are going to show how abstract linear algebra can be. So the first objective is going to define what the rank is and see some of the properties of the rank. Secondly, we're going to try to bridge algebraic and geometric interpretations of problems. This is something we've done in the first two sections as well, and it is a very important skill to have to be able to think about these algebraic expressions that we see with matrices and vectors and try to make sense of them using geometry. So thinking about planes, vectors, lines, etc. We will see how to add matrices, multiply matrices with a scalar, and multiply a matrix with a vector. You may notice that this is all pre-calc material, but we are not looking at multiplying matrices together. So the product of a matrix with another matrix is something that will come out later. Finally, two brief objectives: verify whether vectors are linear combinations of other vectors, and write systems of equations in matrix form is what we will conclude this section. So firstly, what is the rank? The rank of a matrix is the number of leading ones in RREF. So for example, this matrix here in RREF has rank 3 because there are 3 leading ones. There are now 4 propositions that we are going to go over that kind of give us information about what the rank tells us and how to interpret that. So given a system of n linear equation in m variables, its coefficient matrix has size n by m. So in this example, if I bring it back, we have 3 equations. For example, well, it might have been something completely, it might have been 2x plus 7y plus 4z plus 9w's equals 8, but after we work with the equations and reach RREF, it looks now like 1x plus 0y plus 4z plus 0w equals whatever the constant on the other side is. But in any case, there was 3 equations that were given, and there are 4 variables. So in this example, it's a 3 by 4 matrix, but think of it in general as an n by m matrix. So the first proposition is that the rank of A is always less than or equal to n, and it's always less than or equal to m. So by definition of the rank is the number of leading ones in a matrix, and there's at least one, there's at most one leading one per row, and there's also at most one leading one per column. So because leading ones always have to go further to the right than the previous one, there can't be more than the number of columns, and there's always just one per row at most. It could be less if we have a row at the bottom with only zeros. So proposition A is quite clear. There can never be more leading ones than the number of rows and columns. Proposition 2, if the rank of A is equal to n, then the system is consistent. Consistent means that there's at least one solution. If a system is inconsistent, then it means there's no solution. You have a situation where 1 equals 3, for example. So consistent means either there's one solution or there's infinitely many solutions. In both cases, the system is consistent. So if the rank of A equals n, that means that every row has leading 1. I can bring back the same example as before. So in this example, n equals 3 because there's 3 rows, and we can see that the rank of A is also equals to 3. So we are indeed in the situation presented by proposition B. Since every row has a leading one, there will never be a row at the bottom with only zeros, as written here. Remember, it's not necessarily a 3 by 4 matrix. It can be any number of equations and variables. What that means, since there's no row at the bottom with only zeros, that we cannot have an augmented matrix where we have 0x plus 0y plus 0z, etc. equals 7. So that means we will never have a case where there is no solution. If it's not possible to have no solution, then there's at least one solution, which is the meaning of consistent. Proposition C, if the rank of A equals m, then the system has at most one solution. So we are looking for a matrix where the rank is equal to m. In the example that I pulled off before, m was equal to 4. It's a 3 by 4 matrix, but the rank is equal to 3, so 3 is not equal to 4. So let's find another matrix that will satisfy this. Again, it's an augmented matrix. So this is an example of what it looks like. In this case, it's a 4 by 3 matrix. M equals 3, and as you can see, the rank is equal to 3 because we have 3 leading ones. And in this case, the system has at most one solution. So how can we justify that? Every column has a leading one, since the rank of A equals m. That means that no variable is independent or free. We will use the term free variable a lot this semester. A free variable is a variable that you can choose without breaking the system. This also means, therefore, there is one solution, or the system is inconsistent. So how could these two situations arise? If we had only a 3 by 3 matrix, so ignore the last row, then we would have the solution immediately. Z equals whatever the augmented matrix say, Y equals whatever the augmented matrix say, and so on. So that would be one solution. Or, in the example that we see here, a 4 by 3 matrix, there's an extra row at the bottom with only zeros, and so this is going to determine whether the system is inconsistent. If it's 0x plus 0y plus 0z equals 7, then it's inconsistent. Or if it's 0x plus 0y plus 0z equals 0, then that last row gives us no information and we have one solution. So at most, there is one solution. Basically, there is 0 or one solution. Property D, if the rank is less than m, then the system has either infinitely many solutions or no solutions. So in the original matrix that we had seen, the rank was less than m, since the rank was 3 and m was 4, so that's a possibility. The system has either infinitely many solutions or no solutions. In this case, we have what I just called a free variable. X, Y, Z. Z is a free variable. W is set. I have 0x plus 0y plus 0z plus 1w equals whatever the number is in the augmented matrix. But then for z, I can pick whatever value I want. It's a free variable, and that, whatever I choose, will in turn define what y is. And from the first row, it will also define what x is. So if the rank of A is less than m, some columns don't have a leading one. Here's an example. Therefore, some variables are free, so either there are infinitely many choices for these variables, or there is an inconsistency elsewhere. So in the example I talked about, this one here, we see that some variables are free and there are no inconsistencies elsewhere. I'll show you what that looks like in a second. And that means there's infinitely many solutions. The other possibility is like this, virtually the same, but I added a row, so now we have a 4 by 4 matrix. The rank of A is still less than m, 3 is less than 4. But we now have the last part of what is said here. There is an inconsistency elsewhere, at least potentially, because this row of 0 might create an inconsistency. We might have 0x plus 0y plus 0z plus 0w's equals 7, and that would mean there's no solution. So there is no way we have exactly one solution. It's either 0 or infinitely many. Here's an exercise that will encourage us to think about what we just saw above with the 4 propositions. Consider 2 different planes in space. Which of the above propositions corresponds to this case of 2 different planes in space? And what can you conclude? Firstly, if there's 2 different planes, these correspond to 2 equations. So here's this kind of bridging the geometry and the algebra. 2 different planes is a geometric concept, but that corresponds to 2 equations. For example, 2x plus 3y plus 4z equals 9. And since we are in space, that means there's 3 variables, x, y, and z. There is no w in this example. So this is an example of what the coefficient matrix might look like. 3x plus 4y plus z equals whatever, 9, and negative 2x plus 9y plus 2z equals 7. So it's a 2 by 3 matrix, right? 2 equations and 3 variables, and the rank might be either 1 or 2. You could argue that maybe it could be a rank 0, but it is said somewhere that these planes are different, so we couldn't have 2 planes. Well, actually we could. We could have 0x plus 0y plus 0z equals 7 and 0x plus 0y plus 0z equals 9. That doesn't work. So we have 2 different planes, so the rank is going to be at least 1. The rank would be 1 if these 2 rows were multiples of each other. So 3x plus 4y plus z equals 9, and then 6x plus 8z plus 6x plus 8y plus 2z equals 100 million. These would be 2 different planes, but the rank of the coefficient matrix would be 1. And these 2 planes would be parallel. In the case that we have rank 2, that just means that the planes are not parallel, so they intersect along a line. If we have rank 1, we would be in a situation where there's no solutions, right? If 2 planes are parallel, there's no solutions, provided they are different. So propositions A and D apply. A always applies, there's no question about that. The rank is never more than the number of columns or rows. And then D, since we have only 2 equations but 3 variables, the rank of A is always going to be less than M, so there's either infinitely many or no solutions. And in this case, rank 1, there is no solution. The 2 planes are parallel. In the case that the 2 planes are not parallel, they intersect, then D still applies. This time we have infinitely many solutions. And also B applies. B told us if the rank of A equals n, so if the rank is equal to the number of equations, the number of rows, then the system is consistent. It has at least one solution. And indeed, if you think of 2 planes intersecting, there is at least one solution. In fact, there's infinitely many that are all represented along a line. So, let's move on to something that is a little bit more easy now, or we just need to conclude. A system of n equations in n variables has a unique solution if and only if rank A equals n. So think about a system of n equations and n variables. that means n equals m, the number of equations is equal to the number of variables, so the number of rows is equal to the number of columns, and that means propositions B and C apply. So if you look at propositions B and C, one of them says that there's at most one solution, the other one says that there's at least one solution, so that these two together mean there is exactly one solution. Okay, now back to pre-calculus stuff, so things we actually know. Addition of matrices. You can add two matrices entry by entry, so 3 plus -4 equals -1, etc. You can only add two matrices if they have the same order. So a 3 by 2 can be added to another 3 by 2 matrix. Scalar multiplication of matrices. A scalar is a real number. So what you do is you just distribute the scalar to every entry, so 4 times -1 equals -4, etc. A quick easy exercise here: if we have two matrices A and B, we can add and multiply them by scalars. So 10b plus A would yield this value, and 1/2 A minus B would yield this 2 by 2 matrix. Really no problem there. From here on, we are going to go step by step to introduce the concept of matrix multiplication. Matrix multiplication is a little bit peculiar, and it is often parachuted on students in pre-calculus without much of an explanation of where this comes from. So we're going to build on concepts here to reach the idea of matrix multiplication at the end of chapter 2. So the dot product of two vectors v and w is where we're going to start. We've seen that in multivariable there's only going to be one kind of little change here. The dot product is always the dot product, of course, so you multiply entry by entry and you add them together. No surprise at all here. However, we are going to want to be a little careful and most often use a row vector v and a column vector w when we do the dot product. So the vector v dot vector w can be written like this, and so entry by entry it's 1 times 4 plus 2 times 2 plus 3 times -1. And the result is 5. You will notice here that this looks already like matrix multiplication. You go along a row and you multiply along a column, so that is where it's gonna end. Okay. Again, some abstract stuff here with unknown vectors and matrices. We consider a matrix A. So if you look here, this is a notation that we're going to use a lot, and it might throw you off in the beginning. How is that a matrix? Well, the matrix is made of vectors, and in this case, even though it's not specified, the vectors are column vectors. Sometimes we show the column vectors with lines above and below just to show that they extend vertically, like this. And now if you think of vector v1 as a column vector, you may start seeing that A is indeed a matrix. It's a rectangle that has lots of entries, many rows and many columns maybe, and it's just easy to represent all the rows squashed in one by using vectors. So each vector vi is a column vector in Rn, and let's also consider another column vector x, which this time is just a regular notation, so vector x is x1, x2, etc. up to xm. We can extend the definition of the dot product to define the product A times x. So even though it seems like we're splitting hair, it's important to realize that just earlier we've multiplied two vectors together. So vectors are a certain object in mathematics, and now we're multiplying a matrix with a vector. So it's a little bit different, even though vectors are special matrices. This is a little bit of an expanded situation. We multiply a matrix with a vector. But given that we've written the matrix like this, we can just naturally extend the definition of the dot product and say that A times X is going to be A dot product with X, where A is V1, V2, etc. So the product is going to be V1 times X1 plus V2 times X2, and so on. And from here, what could we do? We could rewrite V1 as a actual column vector, V1 like this, and we could just distribute X1 in each of the entries of V1. So we'll see that in a second. So looking at this definition, there's a few questions that are worth asking to help us kind of crystallize all these values and abstract concepts. How many components do the vectors Vi have? So how high is vector V1? And the answer is written here. Vi is a vector that belongs to Rn. So that means Vi has n entries. It's a vector in n dimensions. So the correct answer is n here. Secondly, how many vectors Vi are we considering? And that means how many columns are there in matrix A. And we can see that the last one is Vm. So this gives us the answer. There are m vectors we are looking at. So combining these two first answers, we can answer the third question. What is the size or the order of matrix A? It is an n by m matrix. Finally, describe the product A times X. So is it a scalar? Is it just a number? Is it a vector? Is it a matrix? What's the best answer to this? The best answer is that it's a vector. And we can see here V1 is a vector that I multiply with a scalar. So it's going to give me a vector. And this is going to give me a vector, and so on and so on. So if I add vectors together, I will get a vector. You can say that a vector is a matrix, so this is true too, but really it's much more precise to answer that it's a vector. It's a column vector. So instead of the definition of multiplying a matrix with a vector, we can look at it in a different ways. We can focus on the rows of matrix A instead of its columns. This is going to be referred to later as the note as opposed to the definition. So this time matrix A, the same n by m matrix, instead of being written with column vectors, is written with row vectors. So you can think of it as the same matrix as before, but this time we have squashed all the rows into, or all the columns into one. So V1 is a row vector, V2 is a row vector, and so on. If this is the case, and we multiply by a vector x, we can distribute the multiplication to every row. And we can say that the row vector V1 is multiplied using the dot product with x, and the row vector V2 is multiplied using the dot product with x again, and so we get this expression, v1.x, v2.x, v3.x. And it works because v1 is a row vector and x is a column vector. So let's look at both of these options, the option offered by the definition and the option offered by the note. So this is going to solve the problem using the definition, and then starting again, we can solve the problem using the note. In the definition, we split matrix A, this is A, we split matrix A into column vectors. So this is V1, V2, V3. And the way the definition goes is that we do V1 times 2 plus V2 times -4 plus V3 times 2. So this is what it looks like, V1 times x1 plus V2 times x2 plus V3 times x3. And if you just proceed to computing this, you will see that the answer is 0, 0, 0. It could be any vector. It doesn't need to be 0, 0, 0, of course. If, on the other hand, you decide that you want to split matrix A using row vectors, we will have V1 here, V2, and V3. And for this system, what we do is we distribute vector x to each of the rows, and we use the dot product. So now V1 dot product with x, V2 dot product with x, and same with V3. And if you do the dot products, you will see that you get 0, 0, 0. Of course, it's the same answer. So, two important comments. The first one is directly linked to what we just discussed. Both using the definition of the multiplication of a matrix with a vector and the note work. They are two ways of looking at the same thing, but they yield the same result in the end. The second important or interesting comment is unrelated to this particular situation, but it's just to point out that unlike in regular algebra, if you have x times y equals 0, you know that that means either x is 0 or y is 0, if x and y are two numbers. With matrix, with a multiplication of a matrix with a vector, it is not necessarily true that one or the other is 0. Here, the result of our multiplication was the 0 vector. However, neither matrix A nor vector x were zeros themselves. It can just happen. So what are some of the properties of the vector AX? This is fundamental. It's something that we're going to use over and over again, and actually it is what defines linear algebra. If you multiply a matrix A with the sum of two vectors, it is the same as multiplying first and then adding. Also, if you multiply a matrix A with the product of a certain vectors, it is the same as multiplying the matrix with the vector first and then multiplying by a certain coefficient. So let's discuss why these two properties are true. The ith row of A, the ith row of AX, so if I look at the ith row of this product AX, using the note, it is the dot product of the ith row of A with the sum of x and y. So the dot products, it's the row and the column. And if I look at what this means, it means the first entry in that row, which is entry A, I1, is going to multiply x1 plus I1, y1, and then the second entry in the row of the matrix is going to multiply the second entry in the column vector x plus y, and I can just proceed to do that, and in this step here I am able to separate all the x components and all the y components. So just using standard algebra, all of these are now numbers, so we can just use standard algebra, and we group all the terms that contain xi. And if I look at this row, a I1 x1 plus a I2 x2 and so on, this is simply the ith row of A dot product with x. And the second part here is the ith row of A dot product with y. So from this equal expression, I can just conclude that it is ax plus ay. For the second property, it's going to be very similar. If I look at one specific row of A times kx, it's ai1 times kx1 plus ai2 times kx2 and so on. So now that I have an algebraic expression with entirely numbers, I can use the properties of regular algebra and I can factor out k, which I do here, and that everything that is in parentheses is just the ith row of A times the column vector x. So since this is going to be true for every row of A dot kx, I can say that A times kx is equal to k times ax. Very last part of this long section, a vector B is called a linear combination of some vectors v1, v2 to vm if there are scalars such that B is a combination of v1, v2, vm. So an example is going to be more explicit than these 3 lines of definition. If A is 2, 5, 1, B is 0, negative 2, 1, and C is 2, 1, 3, then we can say that C is a linear combination of A and B. And to justify, we can show that C, 2, 1, 3, is actually 1 times vector A plus 2 times vector B. So since I can express C by using A and B, we say that it's a linear combination of these 2 vectors. We could have also said that A is a linear combination of B and C. You can just manipulate this to show that A is actually negative 2B plus C. And we can also say that B is a linear combination of A and C. Lastly, the matrix form of a matrix is writing the linear equations in a certain matrix form. So here's an example with a system of 3 equations and 3 variables. We can write this in matrix form like this. So we have a matrix A, which is the coefficient matrix, times x1, x2, x3, a column vector, and it is equal to 5, negative 3, 6. So let's just look at one row, 1 minus 4, 3. So 1x1 minus 4x2 plus 3x3 equals 5. So I just read this row here, this column here. Okay, that's it. A lot of content in this section and some very tricky concepts to grasp. It's very hard to understand these things the first time around. We have to review them and just try not to fall too far behind. But these conceptual ideas are what make linear algebra difficult for students in high school. It's also what makes them very interesting and flexible. Thank you.